Hello, my name is Jackson Deeroff, and I'm a junior biochemistry major in Dr. Bill Miller's research lab. Today I'll be talking about my research, which is a molecular dynamics investigation of amyloid beta polyphenol inhibitors in Alzheimer's disease. So Alzheimer's disease is a neurodegenerative disease, so it's characterized by a loss of memory and decreased cognitive function, and it's actually the most prevalent form of dementia. So Alzheimer's Association estimates that about 10% of American seniors over the age of 65, as well as 45% of American seniors over the age of 85 have it. So it's pretty prevalent, and there are two hallmarks to it: amyloid beta plaques, which will be focused on more through this presentation. And these are found typically around synapses, and so they're thought to disrupt neuron communication. And then you have your tau protein neurofibrillary tangles, and these are thought to cut off nutrient transport. And so how do we get these amyloid beta plaques? As you can see here, we have this amyloid precursor protein. It's a transmembrane protein, and it'll undergo proteolytic processing through beta, alpha, and gamma secretases. And so after they cleave, we'll be left with this amyloid beta fibril, and these can aggregate together and form oligomers. When these oligomers are low in concentration, they fulfill their biological role to provide neuroplasticity. And when they're higher in concentration, that's when they typically occur as plaques, and they can lead to Alzheimer's. So a little bit more about this amyloid beta protein. You see 9 fibrils here. Each fibril has has 42 residues. And so you can see that residues 25 through 37 here are highlighted in blue. And that's what we'll be focused on throughout this presentation, because this is where a glycine zipper is. And so what this is that every few residues, there's a glycine. And since they're very small amino acids, they can pack really well, and which helps them aggregate. And so how we are looking at things, we want to see if certain drugs can destabilize it, or if certain drugs can interact well with it. They may provide good insight into how we can further target this with drugs to break up these amyloid beta plaques. So we use all in silico methods, or on computers. So these computers will run simulations and calculations to kind of predict what's going to happen. And so they take into consideration classical physics, so your principles like Newton's laws, electromagnetism, thermodynamics, and they basically just predict binding energies and things like that. So docking, that's the most preliminary step. And so what this is doing is it's throwing a bunch of ligands at the receptor. In this case, the receptor is our amyloid beta. And so it's trying these in a bunch of different conformations to see how spontaneous a certain interaction is. And then we can move forward to further analyze these interactions with molecular dynamics, and then CPP-TRAJ, which helps us visualize it based off of this molecular dynamics data. Same thing with RMSD, or root mean squared deviation, that helps us look at how the structure of the protein changes over time, and then root mean squared fluctuation, which allows us to see how each residue changes. And so our ligands are going to be a group of 11 polyphenols previously suggested in literature. As you can see, they're all pretty similar in structure. As the name suggests, they have multiple phenol groups. And so here are their docking scores. They are all pretty spontaneous. They vary in about 2 kilocalories per mole, but this is not a final indicator. That's why we need to move forward with things to look more into their interactions. So you can see things like resveratrol, which may have a very good binding score, something like negative 6.5 kilocalories per mole, but the RMSD and RMSF graphs show they're pretty stabilized by these ligands. So RMSD here, this is the change in the y-axis, or change in structure, and then x-axis shows over time. So over time, it's not really changing more than the APO structure, which is just the unbound amyloid beta protein. And then over here for the RMSF is the change, and then x-axis is residue number. So pretty much all the fibrils are pretty stable with the resveratrol bound. Each fibril is separated by a black line here. Then you get other things like physatinol with only a docking score of negative 5.3 kilocalories per mole. But the RMSD graphs show that it can destabilize the protein right here around 11 or 1,500 and then around 150 nanoseconds. And then fibrils 1 and 4 become a little more destabilized. And we'll see that in this video here, taking advantage of CPP trash to allow us to see these interactions. So you can see that it starts off pretty uniform, but over time of interactions, these fibrils become more tangled up and disaggregated. So that's something that we may want to look more into in the future. And then you have rosmarinic acid. It has a great binding score of negative 6.8 kilocalories per mole, but it's pretty stable across the board. As you can see, there's a peak here, and as we'll look at in a future video, that's more of a result of it slipping out of the binding pocket a little bit, and the fibrils not being able to interact as well. And then same fibrils that are becoming destabilized, fibrils 1 and 4. And so we'll look at this 0 nanosecond mark for the first few hundred nanoseconds here. And what we can look at is this carboxylic acid here. It's going to pretty consistently interact with this fibril here. And we'll look at this in the future, but it's a result of a couple hydrogen bonds taking place with an asparagine residue. And then here's about the 870 nanosecond mark. And so as you can see, it's not as tight in there. And so these fibrils are just going to become a little more destabilized and kind of get a little crazy for a second. And that's what we get that peak from. But yeah, here's the asparagine 27. The carboxylic acid is deprotonated because we're at biological pH, and pKa of carboxylic acids is typically around 4. And so it's forming a couple hydrogen bonds, one with the asparagine side chain and then one with the asparagine, the nitrogen backbone. And so that's going to be a key stabilizing feature. And so that's what we'll want to look at in the future, is these further H-bond analysis to look at, the formation or deformation of H-bonds over time and, their different locations. And then we'll also want to look at molecular mechanics, Poisson-Boltzmann surface area calculations. So these just give us more binding energy analysis, and then add thioflavin T or THT into the system. This is a common fluorophore used in wet lab, which will be used, after computational methods take place. And so I'd like to thank Dr. Miller, Alex Platt, Connor Bradfield, and Hannah Zimmerman for helping me out with this project, and then as well as Truman State University and Furman University for giving me access to their computers. Thank you, and feel free to ask questions.